Yeah, so maybe you can start this exercise, and this exercise is, as you see, is the same using MODFLOW, running a MODFLOW model by using the ModelMuse graphical user interface. And in this case, if you remember, we already passed through about 2 or 3 examples which were calculated the same by using this ModelMuse graphical user interface. But in that case, we used the grid approach. By meaning the grid approach, from the starting point, we know how many columns and how many rows do we have, and also the shape of our interested area was simple, maybe in that case just a square, rectangle, so we don't have a difficulty to determine how many number of rows and how many numbers of columns do you have. But in this case, it's always recommended to use this conceptual model approach. That is the main aim of today's class, because as you know, our interested area or our study area is not that much a fixed shape, or sometimes it can't be a rectangle or a square or etc. So from the beginning, you don't have the knowledge of how many number of rows and how many number of rows and columns are you going to. So to exercise that one, I already brought this simple example, and for this simple example we are asked to discretize the model by using 100 meters. That means we will have a uniform model discretizations of 100 meters by 100 meters, but at this time we don't know how many number of rows and columns do you have still. And the package that we are going to use, DRN package, which is a drainage package. In the drainage package, we have a shapefile. So the input parameters are already included on the shapefile inside the attribute table. And the recharge package, we are asked also to use the recharge package. In that case, the recharge rate is given 3.8 times 10 raised to minus 9, and the recharge location is the top active cell of the basin. And the evapotranspiration, again, we are given the rate as 3.17 times 10 raised to minus 8, and the EBT surface is the model top, and the evapotranspiration depth is around 0.5 meter, and the EBT location is the top layer. And we are asked also to use 4 aquifers. In this case it says 5, but 4 aquifer layers in which the model top is 0. It means we assume the top surface of that basin is flat, but it's not true always. We have to have the digital elevation model of that area in order to represent exactly what seems like on the top. So model type 0 and the layer 1, or the layer between model top and the alluvial layer is can be model top minus 50 meter, and layer 2 has model top minus 100 meters times 0.85. So I will show you how we can determine the layer depth just by using an equation just to exercise. And layer 3 model top minus 300 meter, and the last layer will have maybe 800 meter depths. And we will have also a variable horizontal hydraulic conductivity for the top layer. So in that case, the conductivity was 5 e raised to minus 5, and 5 e raised to minus 7, 8 raised to minus 7, 1 e raised to minus 8, respectively, from the first to the fourth layer. And assume also isotropic aquifer. It means that the horizontal hydraulic conductivity will be equal to maybe the vertical hydraulic conductivity. That means Kx is equal to Ky. And regarding the aquifer type, the last aquifer is assumed to be confined, but the other 3 aquifers are convertible. That means they are maybe unconfined aquifer. And in this MODFLOW exercise, I already provided you a spatial data set. That means the shape of the basin, and also the shapefile of the river. Please remove this one, a point shapefile. Please remove this one, a shapefile of the river in that case, with the file name river.shp. And the initial head is assumed to be 200 meters. So we are asked to run a steady-state model by assuming all the boundaries are no flow boundary. Then we are asked to determine the distributions of the hydraulic head and also to see the water budget, whether it is converged or not. And those data are just arbitrary data. Maybe we will face a difficulty in convergence. So maybe we will change some parameters later until it should be within the acceptable limit. So in the second case also we are asked to run the same model, but in this case assume a general head boundary in the southern portions of your basin. So all the other three boundaries are no flow boundary, but assume the southern portion as a general head boundary. In that case, the constant boundary was 200 meters, and the conductance can be taken as 0.02. Yeah. So having this, I already provided you the spatial data. The spatial data sets are a polygon shapefile of the basin, that is the study area, and also the river in which we are going to use for a drainage package. So to see what type of data do you have inside the spatial data set, please open your ArcMap and let me see what information do you have on those shapefiles. So open your ArcMap. This is my ArcMap window, which is ArcMap 10.3, and add those shapefiles that I already provided you inside example 3 data. So click on the plus sign and go to the file, and let we see what type of files or what type of informations do you have inside the given shapefile. It's just found inside MODFLOW example file in my case, then MODFLOW example 3. In your case also it is inside MODFLOW example 3. Then you have these two files, basin.shp and river.shp. Yes. Okay. So please open both of them in your ArcMap window. It says there is an unknown spatial reference as a warning. That's okay. Just click on OK. Yes. So this is the shapefile or the basin shapefile we are going to use for our MODFLOW analysis. So as you see here, basically we do have the basin. In this case, that is our interest area, and the rivers or the locations of the rivers, etc. So do you have it? Yeah. So if you have it, let me see what type of attribute informations are included inside these shapefiles. For instance, let me see what are the attribute informations inside the river. So maybe right click on river, right click on the river shapefile, and open the attribute table. Open the attribute table. Yeah, so if you open the attribute table, you can easily examine that we do have the conductance value. Yes, the conductance value is 0.001. The field name is DRN conductance 1. It means a drainage conductance 1. So the conductance is 0.001. And the drain elevation can be taken as the model top. And the formula is again the model top. Imagine when we are using this drainage package in ModelMuse, we are going to use those data as an input. Yeah. If you are okay with that, please open your ModelMuse. Again, we are going to import those shape files on the ModelMuse. On the ModelMuse. So please open your ModelMuse again. Yes. Yeah, we are going to create a new ModeFlow model. So click on new ModeFlow model option. Then click next. Click next. Maybe you can write the description if you like. If not, you can pass this step. Maybe I can write conceptual model approach or GIS approach. Conceptual or GIS approach. The simulation starting date is today, so you can select today, which is 12/24/2018. Then click on next. Click on next. This is a place where we make a difference. If you remember last time, we know the numbers of columns and the number of rows that we have, and also we specified the numbers, the column widths and the row widths again. But in this case, we don't know how many numbers of rows and how many numbers of columns do we have. But we have the information how many numbers of layers do you have. We have 4 numbers of layers. Maybe you can change this one into 4. And you can specify also the depth of your aquifers. In that case, the model top is 0 meter, and the upper aquifer, all the alluvium is model top minus 50 meter, so leave it as it is. And layer 3 has also model top minus 30 meter, and layer 4 has 800 meters. So leave as it is because we don't have the option to write those equations here at this step. And the next thing what you are going to do is you don't need to produce a grid. If you remember last time, we already specified numbers of columns and also the widths that we have, then we finish. And in that case, the ModelMuse maybe will display the numbers of grids and numbers of rows that we have. But at this step, we don't know how many numbers of rows and how many numbers of columns do we have inside this polygon or inside the basin shapefile. So in the conceptual model approach, you have to say no grid. No grid. Click on no grid. Yes. When you click on no grid, you have nothing on the top view of your ModelMuse window, no? Because you already specified as you don't have any grid on the top. Yeah. So the next thing what we have to do is we have to import the shapefile that I already provided you. So to import the shapefile, please click on File, go to Import and Shapefile. Click on Shapefile, and you know where you have the basin shapefile, the one that I provided you already inside ModelFlow example 3. So go to your file location. In my case, this is a location. It says ModelFlow example 3. So double click on it, then the basin shapefile. The basin shapefile. Then open. Then click on open. 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 So you are importing the basin shapefile. So click on set values of enclosed cells. Set values of enclosed cells. Again, the Z formula, that is the formula for the vertical distributions of our aquifer. As you remember, you have 4 layers, so it should be from model top to the last layer. So click on 2. Then edit formula. The higher Z coordinate is the model top, so edit the formula here and go to data sets, required, layer, and model top. Just double click on it, then OK. So the higher Z coordinate is the model top, and the lower Z coordinate will be the last aquifer, the bottom of the last aquifer. So edit and click on lower aquifer button. Lower aquifer button, then OK. Just double click on it, then OK. It means you are defining as the depth of your aquifer on the basin. That means from the model top to the last layer. Then click on OK. Click on OK. And one thing, sometimes it's good to check what type of data is included. So click on data, and if you click on data, there are active, object name, the formula, high Z, and low Z. Imagine those datas are the attribute table what you see on the Shapefile. For instance, go back to your ArcMap window and check the attribute tables of your basin. Right click on the basin and open attribute table. Look, so the attribute table on your basins are the ID, the shape, the active, the object name, Z formula, high Z, and low Z. Yes? So those are the information which are displayed here. So it means these informations are just the attribute data of your Shapefile. Maybe they are not that much useful in this case, but I will show you maybe when we are like this river Shapefile, those information should be checked. That means you have to check all of them. In this case also, you can click on select all. Select all. It means selecting all those data sets. So click select all. So selecting all of them, no? Then click on OK. Click on OK. Look, we specified, but again, we don't have again, you do have nothing on your top view of the model. Yes? Yeah. Imagine we already imported the Shapefile, but still we don't have the grid, even we don't have our basin on the top view of the ModelMuse window. Then click on show or hide objects. This is show or hide object option, because we had already the Shapefile basin, so it means we have one object. So click on that, and click on datasets, user defined. So this is the Shapefile that we added already. This is the Shapefile, which is basin.shp. Double click on it, being here. Do you have it? Just double click on basin 1 and you will specify the object properties. Yes, double click here and we are going to specify the object properties. That means we are going to tell the software with how we are going to discretize, with how many columns and rows, and also watt meter. Like we in the exercise, it's specified that the discretization should be uniformly with 100 meter. 100 meter. So this is a place where you specify the grid cell size. So click on use to set grid cell size option and put it 100. Yeah, so click on OK. Click again on OK. Still, you don't have nothing on the top of the ModelMuse window. The next thing what you have to do is click on generate grid option. This is the generate grid option on ModelMuse window. Click here. Yeah. So here the first option is calculate grid angle automatically. It means that based on the shape, if you remember, this is your shape of the basin. So based on this shape, maybe the ModelMuse will create a grid, but in that case it's not maybe a vertical grid, maybe with 10 degree angle or 20-degree angle, etc. But we don't need that. We don't need that. If you are not interested to make a vertical grid, you can check this one, calculate grid angle automatically. But if you need a grid angle to be 0, so uncheck this one. That means the grid angle is 0. We will expect just a vertical grid, no? So click on OK. Click on OK. Now you will have your basin with 100 meter and 100 meter grid cell size. That's why I told you, you don't know how many numbers of grids do you have inside your basin, no? And from the grid approach, it's difficult. That's why the conceptual model approach or the GIS approach is preferable in the real world project or in the real world research. So if you count them, we do have so many numbers of rows and so many numbers of columns, but we already discretize uniformly by using 100 meter. 100 meter. So if you are okay with that, you can check also you have a 4 layer. But it showed me here 3 layers. I don't know why. Anyways, let me proceed. So we already specified the numbers of grids and numbers of rows that we have, and also a uniform grids of 100 meter. But think our study area is the polygon. Let me make the polygon maybe with different color. In that case, you can identify. So the color object line, maybe I can make it green. Yeah. So this is the basin Shapefile that we have. It means the grid inside the basins are the one the calculation should be based on. We don't need the outer grids which are outside the basin shape. So how we are going to fix that? How we are going to tell the software use only the grids which are inside the basin, but leave the grids outside the basin shape. In MODFLOW or in ModelMuse analysis, the grids which are inside your interested area, they are called active grids, but the one outside your model area, they are inactive grids. When you click here, or if you click here, you have the option of show active, show all, show exterior, and also show active edge. So how we are going to tell the software those grids inside the basins are active, but outside are inactive. So the first thing what we are going to do is we have to specify the whole grid as a false value. By meaning false value, they are inactive. Then again we'll come back and tell the software those grids inside the shape are true values. By meaning true values, they are active. So to do that, click on data and edit datasets. Then go to required and expand the hydrology by clicking on the plus sign, and you have the options of active. Yes, click on that, and you can see here it says it's true, but it should be false, because we are dealing the whole basin. So write here false rather than true, F-A-L-S-E. By meaning false, we are telling we don't have any active cell. So click on apply. Look. Now again, just click on objects and datasets, user defined and active one. Double click here. Yes. Then go to datasets and required hydrology active. Look, this is again, it is false, but it should be true. That is the basin shape. So change this one into true. Then click OK. Now we specified which is active and which is inactive. To check whether it works correctly, click on here, show or hide 2-degree lines, then click on show active. Yes, so this is the active cells, but the cells outside are inactive. This is the active cells which are inside your model or inside your basin. If you are okay with that, the next thing is we have to specify the Aquifer parameters, and also we have to import the river shapefile that we have. Then after rearranging all the MODFLOW package, maybe we will run our model and we will see what result do you have. So import again the river shapefile. You know where to find it. So click on File, Import, go to Shapefile. Then you have river.shp. Open. Then select set values of intersector cells. Select set values of intersector cells. And specify the Z formulas for your river. If you remember in your ArcMap window, and if you right click on the river and check the attribute table, you can see what is the Z formula for the river. So here the Z formula is model top, no? The Z formula is model top. That means your river is on the model top or on the top surface of your basin. So come back here and click on 1 because it's just model top. Then edit function and check the model top. Then OK. Then OK. Then click again OK. Now you have your river on the top of the basins. I don't know if it is visible. Maybe let me change the color of the river. I can double click here on the object and I can change the color into blue. Now you can see the river on the top of your basin. On the top of your basin. Still now we are not specifying which package are we going to use, but we already imported the river Shapefile. And in MODFLOW, you can use the Shapefile as a river package, or you can use it as a drainage package based on whether your river is a gaining river or maybe a losing river. By meaning a gaining river, this river can get water from your aquifer. In that case, the water tables of the aquifer is maybe above the levels of your river, so that river may gain water. So if your river is a gaining river, in that case assume that river, or you can use the MODFLOW as a drainage package. If not, you can assume by using a river package. So in this case, it's asked to use a drainage package, so we are supposed to use DRN package. The next thing is specify what types of package are you going to use. So click on models and click on MODFLOW package and programs, and as per the example, it says the packages are drainage package, recharge package, and evapotranspiration package. So we have 3 packages inside the boundary condition. So click on the boundary condition and specify flex, check the recharge package. Check the recharge package. And if you remember on the example notes, it says when you use the recharge package, the recharge location is top active cell. That means here the recharge location option is the top active cell. The top active cell. You don't have groundwater well, so you are not going to use a well package, but you are supposed to use evapotranspiration and drainage package. Those packages can be found inside the head dependent flux option. So expand head dependent flux option. And the first is drainage package. We need drainage package, so check the DRN package. And again, go down and check the evapotranspiration package, which is EBT. EBT. Check again the evapotranspiration package. Again, on the example note, it says the evapotranspiration location is top layer. So the default top layer is okay. No? So that's okay. So those are the package we are going to: the recharge package, the drainage package, and the transpiration package. So click on OK. Click on OK. And if you read the package information in the example, it says the drainage package use the river Shapefile attribute field values for elevation and bed conductance. It means on the Shapefile, inside the attributes, as you already observed, we had the elevation and similarly the conductance value. The conductance is 0.001 and the drainage elevation is model top. So we are going to specify those information just by using the function option inside ModelMuse. Look, here it's very easy just to write the conductance is 0.01 and similarly the drainage elevation is model top in your ModelMuse window. But you have to know how you can call those information from the attribute tables of your Shapefile. This example is just very simple. You don't have lots of data, but sometimes you face with multiples of data. In that case, you have to know how to specify those informations by using the function option in ModelMuse. So next, I will show you how we can fix those items. So as you know, we are going to use this shape, the river shape, for our drainage basin. So double click on it, double click inside the drainage option or the rivers object. Let me go back again and let me do it again. Double click here, double click here. Then this is a river. We have to specify the model flow features. Yes, when you click on the model flow features, you have those packages in which we selected previously. Out of those packages, we are going to use the drainage package or DRN package. So check the DRN package. Look, what information or what data do we need to run the drainage package is you have to know the elevation, and again you have to know the conductance of the bed material. We know that the conductance is 0.001 from here, yeah, and the drainage elevation is model top. So it's easy to write. It's easy to write here 0.001 and also model top. But let me show you how we can use the function to specify those items because they are very helpful. To specify, maybe click on the function here. Yeah. And use the function options again here and expand it. And go down and select object. Now we are going to tell the ModelMuse use the elevation values from the Shapefile that you already imported, and inside the Shapefile we have an attribute table in the object which had an elevations of model top. So click or expand the object option here by clicking on the plus sign. Then go down and select object imported values are. It's simple. We are going to tell the software, please use the elevations of the drain with the imported value. So double click on it, double click on it. When I double click on it, it will come here on this formula editor. So double click on object imported value R. Yes. So which value the software is going to use? Object imported value, but which one? When you see the values, the Z formula or the Z formula is model top, no? Model top. So go back to your ModelMuse and scroll up again, scroll up and specify model top. So double click on it. When you double click on it, it will come here in the place of key. It means you are telling the software use the already imported object value of model top. Model top. Do that. Or the other option is you have to give the Z formula field name. It means go to user defined and create from Shapefile attributes, and you have the Z formula, or you have to give the model top and double click on it. When I double click on it, it will come here, and if it is correct, the formula editor window will write on this place. If not, it's not going to write it here. So double click on model top. Now still you have a problem because there is no any on the formula editor. So maybe so it means object imported value R is the model top. The model top. So click on OK. Now this is just model top, object imported value model top. And again, specify the conductance. You know the conductance is 0.001. So maybe you can write 0.001 here, like 0.001. That is the easiest way to give an input. But you have to know again how we can give by using the function. Because if you have a series of data like 100 conductance value, it's difficult to put or to insert all of them manually. So it's better to use the conductance values by using the function window. So click here, and again go to the object and object imported values are. Then you need the conductance. So click on user defined, create. As you see here, you don't see any conductance information, no? It's only active one, high, low Z object, Z formulas. You know why? Because those informations are for the Bayesian Shapefile, but we haven't checked the field values of the river. So to specify that, go back again, and double click on it. double click on it, and data sets, and check sorry, let me check whether it is. Yeah, let me double click on it, and still it can't show me the imported shapefiles attribute tables or attribute values. So in this case you can specify just by using 0.01 in your drainage package. So the time is from -1 to 0. That means we are going to use a steady state simulation, no? Then please specify the conductance 0.001, 0.001, and the elevation value is a model top again, model top, then click on OK. And the conductance interpretation, as you see here, is the default is calculated. Maybe you can change it direct if it is direct, or a total per year for each layer if it is for total per year for each layer. But in this case, leave it as it is, that is calculated. Then click on OK. Click on OK. Yeah, we already specified the drainage package. The next thing is we have a recharge package and evapotranspiration package. And it says the recharge package, the recharge location is the top active cell, and in evapotranspiration package, again, the evapotranspiration is the top layer. It means to specify the recharge and evapotranspiration, we have to add again the shape files of the basin. So click on File again, Import, Shapefile, Basin, then open. Set values of enclosed cells. Now we are going to use the recharge package. So for recharge package, the recharge location is top active cell. So we don't need maybe a Z formula. Then click on OK. Yes. Click on OK. Just to differentiate, maybe I can put the color object interior by using this one for you to visualize. Yes. So we are going to specify our recharge by using the basin shapefile. Those data are already provided. The recharge rate is 3.8 10 raised to -9, and the recharge location is 2 active. So double click on the basin or the object you added now. Then click on MODFLOW and put it RCH or recharge package. The time is again from -1 to 0 because it's just a steady state. And here is the place where you specify the recharge rate. The recharge rate from the example is 3.8 e raised to -9. So 3.8 e raised to -9. 3.8 e raised to -9. Click on OK. Now you already used your recharge package. What we left is the evapotranspiration package. Again, import the shapefile, or maybe you can specify by using the already imported shapefile. But to differentiate, just import the same shapefile, and basin. Then open, and set values of enclosed cells. Yeah, and click on OK. Now you have, or you added maybe around 3 basins, you see, with the file name basin. But basin 3 still is not used. So let me double click on it. And let me change the color again for you to identify. It is just evapotranspiration. Let me make it this color. And click on more flow features and check evapotranspiration package. This is the place where you specify the evapotranspiration parameters. Again, it's just a steady state flow. So the time is maybe from -1 to 0. And the evapotranspiration rate is just already specified. The EBT rate can be taken as 3.17 times e raised to minus 8. So 3.17 e raised to minus 8. And the evapotranspiration surface is model top. So click on function, and it's just model top. Then click on OK. And the evapotranspiration depth can be taken as 0.5. It's already specified on the example, so you can write here 0.5. That is it. So click on OK. Yeah. So we have those 3 packages as you see here: the drainage package, the evapotranspiration package, and the recharge package. We already specified our package. What we left is specifying the aquifer properties. That means the depth of your aquifer and also the horizontal conductivities of your aquifer again. So where to specify that one? Go to data, and click on edit datasets. And expand the required option, and again expand hydrology. This is the place where you can specify your Kx, Ky, Kz, and also the MODFLOW initial head. The MODFLOW initial head is already specified on the example. It says MODFLOW initial head is equal to 200 meters. So first let me put the MODFLOW initial head 200, and Kx value, it says we have variable horizontal hydraulic conductivity of, we have 3 values: 5 e raised to minus 5, 5 e raised to minus 7, 8 e raised to minus 8, and 1 e raised to minus 8. Look how you are going to specify it, because here you have only one value, no? But the hydraulic conductivity that we have is variable. It means it's different for the first layer, for the second layer, for the third layer, and again for the fourth layer. It means you have to use the formula editor, and you have to use the case, the if case. That means if it is for layer 1, use 5 e raised to minus 5. If it is for layer 2, and if it is for layer 3, and again if it is for layer 4. To specify that one, click on edit formula option, click on edit formula, and again expand the function option. Yeah, and here you have a logical option. Expand the logical option and you have case. By meaning case is just if function. So double click on it. Yes. So when you double click here, you have the keep function. It means if the case, in our case is layer, for layer 1, you have to specify the first 5 raised to minus 5, layer 2, 5 raised to minus 7, layer 3, 8 raised to minus 8. But what is the index? In this case, the index is a layer, no? Because the argument is if you are in layer 1, use K1. If you are in layer 2, use K2. If it is in layer 3, use K3. And if you are in layer 4, again use K4. So our index is a layer. So to specify the layer, click on grid or mesh. And when you go down, you have a layer option. So double click on it. Double click on it. Now when you double click, the index is converted into layer. Now here in the place of result, write the first hydraulic conductivity, which is 5 e raised to minus 5. 5 e raised to minus 5. And in the place of result 2, write again 5 e raised to minus 7. Again here you have 3, so write 8 e raised to minus 8, which is the third one. And again comma and write 1 e raised to minus 8. Like I said, if your formula here is correct, it should be displayed here. If not, that means the formula is incorrect. So maybe it's not displayed due to those dots, those 3 dots. Maybe I can reduce them. Maybe I can remove 1, 2. Now the formula is correct. It means the horizontal hydraulic conductivity for the first layer is this one, for the second layer, for the third layer, and for the fourth layer. Then click on OK. Click on OK. So the horizontal hydraulic conductivity is specified by using the formula. It's also mentioned that assume isotropic, by meaning isotropic, kx is equal to ky. So by default, ky is kx and kz is kx over k. That's okay. And we specified already the MODFLOW initial height, which is 200 meters. That's okay. Next, specify the layer definition. As you see here, we have around 3-4 layers. So the model top is 0. So click on the plus sign on the layer definition. The model top is 0, the default. But assume if your model top is flat, maybe when you draw the water table, you have high probability of the water table to become above your model top. But always your model top should be the digital elevation model. I'll show you in some other exercise how we can fix the model top, the dim, and how we can interpret those values. Then the upper aquifer bottom, it says it's just alluvial. We haven't specified the name. It should be specified when we start the project. But the alluvial depth or the upper aquifer bottom depth is model top minus 15 meters. Yes, it says model top minus 50 meters. So here you have to specify model top minus 15. To do that, click on edit formula and specify model top minus 15. You have your model top here, Just double click on it. Then you have minus sign, minus, and 15. You can write either from your keyboard or maybe you can write here. It means the first layer depth is the model top minus 15 meters. 0 minus 15 is, it means it has 15 meter depth. Click on OK. So the upper aquifer bottom has model top minus 15. And the middle aquifer bottom is already specified that layer 2 has model top minus 100 meter times 0.85. If you read the example, it says layer 2 is model top minus 100 times 0.85. So we have to specify here again by using the formula editor. So click on edit formula. It's just model top minus 100 times 0.85. So again, you have to make those brackets. Maybe we need 2 brackets, and it's just model top minus 100. Then maybe you can close 1 bracket and times 0.85. You can write 0.85 from here or maybe from your keyboard. Then close the bracket. When you close the bracket, it's just displayed here. It means the formula is correct. Then click on OK. Now you specified the depth of your middle aquifer bottom and specify the lower aquifer bottom again. Here on the exercise, we were supposed to use 4 layers, but unfortunately we use 3 layers here because we haven't specified when we start the project. So let we use this information of layer 4. It's just 800 meters. So right here, 800. Right here, minus 800 because we did minus. That is it. So you can say apply. Apply. What's left? We already specified the package, the aquifers. Okay, the aquifer horizontal conductivity. What we left is the aquifer type. The aquifer type, it says the last aquifer is confined and the others are convertible. So where to define our aquifer layer groups? To define, click on model and go to MODFLOW layer groups. MODFLOW layer groups. So the upper aquifer, it says convertible, and the lower is, or the middle is convertible, but the last one is confined. No, it's already specified here. The last aquifer is confined, but the other are convertible. So put the last aquifer confined, that's okay. The middle aquifer convertible, so click here and convertible. And the first aquifer or the upper aquifer is again convertible. Then click on OK. One thing what you have to take in mind is that we haven't specified any boundary condition yet. If you leave the MODFLOW project as it is, and if you run your project, it means the system automatically will understand no flow condition. The boundary is no flow condition. It means there is no flow outside or inside all boundaries of your model. That's why we ask it on the number 1, it says run the steady-state model using no flow boundary. So we have to run this model as it is, and we have to check the result. Like I said, we will face a difficulty maybe. By meaning difficulty, it will not converge, or the budget will not have maybe an acceptable limit. So let's run this model and we will see what will happen. So before running, it's always advisable to save your ModelMuse project. So to save that one, click on File and Save. Or maybe you have the Save option here. The Save option here, or the Save As option. So click on File and Save As, and let me save the whole ModelMuse project. I can put it inside ModelFlow example 3 and with the file name maybe class exercise 3. It's good to save because sometimes when you run your model, you'll face difficulties or maybe the system will fail. In that case, you don't need to re-input all the input parameters. Rather, you can open the saved ModelMuse project. So click Save. Now you already saved your project with the file class exercise 3. Next time you face a difficulty, just you can double click on it. Then you will have all the information as it is. So if that is the case, I think we already import all the required parameters. So maybe we can run our model and let me see what will happen. So this is the run ModelFlow option. And here, when you run your model, you have to know which ModelFlow program are you going to use, or which ModelFlow program you have on your computer. If you remember, I already provided you ModelFlow NWT, yes, last time. You can use ModelFlow NWT or ModelFlow OM, which is the groundwater hydrologic model. Let's use ModelFlow NWT. Then, to use ModelFlow NWT, you have to specify the solver, and the solver should be Newton solver. So assume you are going to use ModelFlow NWT. So first you have to tell the software I am going to use ModelFlow NWT. So click on Model, then ModelFlow NWT. Click ModelFlow NWT option. Look, it's just a very useful information. Sometimes if you forgot, it's telling you that now might be a good time to activate the upstream weighing flow and the NWT server package. Yes, if you use ModelFlow NWT, you have to make the upstream weighing and the NWT server package. Don't forget that one. If it is OM, you don't have to specify that one. You can use either another solvers, and you can use also LPF. Yeah, so you have to specify that one. Click on OK and click on Model and go to ModelFlow package in Programs and specify that one. If you remember, if it is NWT, it should be upstream weighting package rather than LPF. So click here and again go to the solver and use the Newton solver. Solvers, Newton solver, automatically selected, that's okay. If not, you have to check the Newton server because you are going to use the ModelFlow Newton program. Then click on OK. Now it's ready to run your model. Let me see what will happen. So click on the run option. This is run ModelFlow NWT option. Click on that. Maybe you can save with a file name class exercise 3, that's okay. So I can say save. And you can specify the program location. I don't know where I have the ModelFlow NWT program. Maybe I can check inside C. And program files. Then ModelFlow NWT. So as I can see here, I have ModelFlow on, but I don't have ModelFlow NWT. I have ModelFlow NWT in my hard disk, but I don't want to maybe add here. So in my case, let me use MODFLOW in my case. Okay, in your case use MODFLOW NWT. So LPF and the solver, what I am going to do is PCG automatically. When you convert from NWT to ohm, it already changed the solver. So maybe I can use a zip or stringly implicit package. Then I can say okay, then run the model. The file name is okay, class exercise 3, then save. Yes, now it's just running the model. Yeah, as you see here, it's just red. By meaning red, you have some problems. And the problem here, the running process is not terminated correctly maybe, and I have some listing files. Cell conversion for item 3, layer 1, blah, blah. It's just a conversion problem. It means maybe some cells are dry. That's why it will result in a problem. So when you close this one, you can see the budget, and it's not still calculated the budget because it faces some problem. It means you have some errors. So you can find the errors, and the warning is here, and the warning is it's just missing a georeference data. There is no any problem regarding this one, but you can check error and warning is still we don't have errors, but it can't converge. Maybe let me change some parameters. In that case, we will run the model again. So I can put maybe here 100, and let me run and let me see what will happen. Yeah, still there are some problems, and the problem is here it says divide by 0 in SIP at a layer 1, okay, row 238 colon 90. So let me go to MODFLOW package and programs and solver SIP. Maybe I can increase the numbers of iteration here, or the change criteria. Just let me put this one into 500. Still we have some warning, and let me check the model. Like I said, those are just a random data. So if you have a random data, you face a problem because the model can't converge. Again the same. So let me change another data just to check the parameters. Sometimes the cell will become dry and it's difficult to have a result. Huh? It's still the same. but it ran in the past from 2000 to 46,034, but still there are some problems. But still you have your result. When you go down at the end, this is just your budgets, volumetric budgets. So you have your budget components, the inflow component, and similarly the outflow component. The percent discrepancy is minus 1.1. This value should be good if it is near to 0. So again, you have to work until this value is approximately 0. That's why we need a calibration also. But I'll come up later. That is another issue, how we can calibrate and how we can say our values are true. But in this case, your model is already terminated normally. That's okay. Maybe you can answer the first one. It's not converged. Was the budget convergence within the acceptable limit? It says. So the answer was no. It was not within the acceptable limit because it is like minus 1.1. It should be very near to 0. But from here, it was also asked that find the distributions of the hydraulic head at the end of the steady state period. So you have already the distributions of the hydraulic head. So let me see the distributions of the hydraulic head. So maybe I can minimize all those things. And you know where you saved your file. Yeah, here those are the results. Those are the results. Class exercise 3. Class exercise 3. But what we need is to display the hydraulic head distribution. How we do that? So go to your ModelMuse window here and display by importing your result. Here it says import and display model results. Import and display model results. So by clicking this one, we can import our model results. But to do that, let we uncheck all those objectives. Now we don't need them. So maybe I can uncheck the drainage, I can uncheck this one, and I can uncheck the recharge. So this was our case. So let me import the hydraulic head distribution. So click here. If you remember, the one with .fhd extension is the hydraulic head, and the one is .fdn extension is the drawdown, and you have also some other results inside the .cbc. So click on class exercise 3.fhd and click on open. Yes, you have one result because you ran a steady state simulation now. So let me check the contour grid option. Click on contour grid and click on OK. Click on OK. So those are the hydraulic head distribution. That is a calculated hydraulic head distribution. It says it's around 99.56. So as you see here, the output is not convincing. It can't be like this. But at this point, you have to know how to build a model and how to run the model. The accuracy and the calibration, etc., is another issue. So maybe this is the distributions of the hydraulic. It showed me a constant head all over the place. That's not correct, but it's okay for the time. So maybe I can change the contour interval into 0.5 or maybe 0.1. Oh, it was 0. Yeah, it showed me like a constant head. I don't know why, but as this step you have to know how to build the model and how to run. Maybe the accuracy, etc., are another issue because those data is just a random data. So maybe you can have and you can answer the first equation, and you can import also another result just by clicking on imports, and you can import FDN, or maybe you can go to the class exercise CBC and let me check what information do you have inside. So click here and click on open. Yes, so here inside CVC you have the evapotranspiration, the drainage, and also the recharge. Let me see what was the evapotranspiration. So maybe click on evapotranspiration and click on color by doing the color and okay. Yeah. Yeah. So this was the evapotranspiration values for the whole basin or for the whole steady area, and it showed me the evapotranspiration was all over zero. Again, there are some problems still because of the convergence, etc. And again, let me click the recharge. Again, click here and class exercise.cbc and recharge. Let me check. By using a color grid. Again, those are the recharge distribution values. Those are the recharge distribution. You can see on the 3D here the recharge layers. Yeah, those were your shape files, and you can see the recharge and evapotranspiration distribution also in your shape file. So maybe you can answer number one just by like this, and number two it says run the model by assuming a GHP, a general head boundary, as the south of the study area, and compare the result. Compare the result with this one, and use a constant boundary here 200 meter and a conductance of 0.002. So you can specify a GHP, a general head boundary, as a southern border of your model. So you have like a regular shape. So maybe south means maybe this area, maybe from here to here, I don't know, or maybe from here to here, that is south on the southern portion, because you don't have a regular shape. So how you specify the general head boundary in this case? To specify a general head boundary, again, you can have the object and you can specify the object property, but maybe let me remove first the evapotranspiration and the recharge that I already added. So maybe I can go to color and I can make this one none. Yeah, so now we are okay, no? Yeah, so let me put randomly a general head boundary as the southern portions of your model. So let me decide again the southern portion, maybe to start from here, maybe from here. No, let me to make it short, from here and up to this point, maybe. Yeah. So click one object from here, and that object should be again a polyline, no? Because we are going to draw a polyline. So click on create polyline object, and you can select the last grid as maybe a GHB. So I can click here on polyline. Let me decide the GHP boundary start from here. So you can click here, go again until there is a change in direction. So go down. Then again, you can select this one, and you can go to here. And this one, maybe this one, and this one until you get the horizontal. So maybe I can select this one to make it easier. Maybe I can go down. So let me say this is enough, but always you have to specify your boundaries correctly. In that case, it's good to specify by using a shapefile, because if you have a shapefile, you can drop it here. You don't have to draw like this. So when you finish, maybe you can double click. I can double click here, and I can specify my shapefile. Let me put the boundary into 2, that is from the model top into the last aquifer, that is the lower aquifer bottom. And maybe let me change the color into red just for a better visualization, and position lock for not moving. Then I can say okay. Still I haven't specified the general head boundary package. I can say okay. That means this is the boundary, let's say the 1000 boundary. Then go to your MODFLOW package and programs, and activate the general head boundary package. So click on boundaries and click on head dependent flow boundaries. So go to until you get general head boundary package. So activate the GHP package, then okay. Now you can double click on your boundary object, that is the one with the red. Double click on it. Now click on MODFLOW features and select general head boundary. So the starting time is from -1 to 0, the same, and the boundary head and the conductance is already given. And number 2, it says use a constant boundary head of 200 meter and a conductance of 0.02. 0.002, sorry. So click on OK. That is your GHP. That is it. And run your model again and compare the results. Those results. Yeah. Compare your results, your budget, your water budget, etc. So run your model. Let me put class exercise 3, maybe with general head boundary, just to identify from the previous file name. So I can say save. The space character are not allowed in the name, okay. So because I use the space now, maybe GHP, I can add GHP like this. Save. Then yes, now the model is running. And let me see if it converge, and also we can compare the result from the previously run model. Now look, it's just 0. My meaning 0, our model is converged. So you have to compare that. Specifying the boundary condition is a very critical thing in the MODFLOW modeling process. If you remember, in the first one, we were in difficulty because it can't converge, because all of the surrounding were no flow boundary. But now with a single general head boundary, the water has the capacity to move out from the system and to come up and join the aquifer. That's why we have a normal termination, and the percent discrepancy is 0 again. So you remember these were our results for the first one. In that case, the percent discrepancy is minus 1.21. But now you have a result with a percent discrepancy of 0 if you go down. It's just minus 0.001 minus 0.00, which is approximately very near to 0. And your budget is convergent, no? That means you have a balance, a water balance. The inflow is equal to the outflow. That means you can compare the total inflow is 3536 and the total outflow is again 3536. That means inflow minus outflow is 0 because we run a steady state simulation. In that case, we don't expect any storage change. So inflow minus outflow value is 0. So you can check again also the result. Let me call the hydraulic conductivity, the hydraulic head values. So the hydraulic head value now again is maybe different from the first one. Let me see. You look, now it seems like a true value. If you remember from the previous or the first run, we had a constant values, but now you have also a different values rather than the constant. Let me change 0.5. Yeah, you can see 109.5, etc. Or let me put it 0.5, that is a contour interval. And now you can see those hydraulic head distributions as a different point. It seems true values in comparison to the first one. So maybe you can answer the second exercise just by like this, and you can compare from the first question. I think you know so many things, how to add and also how to run, how to specify different packages, and how to use a conceptual model approach. That means how we can import a shapefiles into the ModelMuse window and how we can run our model. So this is the normal procedure in order to run and to use a MODFLOW project. So maybe you can use your own data and you can maybe exercise as it is. So you can import and export also your result. For example, you need these hydraulic head distributions in your report. Maybe you are writing a report in a Word document, so you need the result. So how you are going to use those results in your document? So first you have to export the result. Let you export, for instance, the hydraulic head distribution. So click on File and you have the export option. File, export, and go to Shapefile. Go to Shapefile, and it says contour to Shapefile. Click on that, contour to Shapefile, and save it with the file name, maybe hydraulic head. Hydraulic head. Save. Now you can call your results, whether if you like in your ArcMap or any other geoprocessing, or maybe in QGIS, etc. Add the calculated head distribution. Here is. So add. Yes. So this is your hydraulic head value. This is the calculated hydraulic head distribution. Maybe you can change and you can increase the size for a better visualization, and you can label and you can see also the values. the value. So those are the hydrogen distribution values in your ArcMap window. So how you are going to put it in the Word document, you know how to produce layout in ArcMap, no? Yes? Yeah, so you can click on layout view, layout view. So those are your maps. Maybe you can come back to your data view, and you can increase the size and go back to your layout view. And also maybe you can increase your borders. You know how to do that, no? In ArcGIS. Maybe let me increase again the size. Let me reduce it back. Yeah, maybe if I'm satisfied with that, then maybe you can insert also your north arrow. You know how to insert north arrow. I prefer this north arrow. Okay. Yeah, this is a north arrow. Maybe I can put it here. Yes, so you can insert also the scale bar. So maybe if I need, this is my scale bar. So መጀመሪያ ጂኦ reference መሆን አለበት. That is the case. But if it is a scale bar, you can put your scale bar here. You can increase the size. And maybe that's a scale bar. Then you can export. If you are okay with that, then go to file and export map. Yes, go to file and export map. So in this case, you can save your file by using a PDF or by using an EMF. Always, when you export your file from ArcMap, and if you want to put it into a Word document, it's good to use EMF, because in the Word document, you have the capacity to insert directly. If you saved it in PDF, maybe the PDF document is very big, your image is very big. In that case, you have to cut or you have to clip and you have to put it into your Word document. By doing that, your quality or image quality will reduce. And again, when you export in ArcMap, take care of again the resolution. The default resolution is here is 600 dpi. If you want to insert your document for publishing a paper, they use your image quality, and always they are asking a dpi of greater than 300. So maybe 600 dpi is okay. So maybe I can change the file name again, class exercise as 3, and I can save it inside exercise. Where is it? MODFLOW exercise file inside MODFLOW example 3, then save. And like I said, let me try save as type as EMF. EMF. Check on the internet what we mean by EMF, okay? Then save. Now you have your EMF file, saved EMF file, that is this one. That means this one. So what are you going to do is you open your Word, your Microsoft Word, and directly you can insert the image. Insert picture, then go to the file you saved it. It is just inside groundwater course and inside example 3, and maybe all files. No, sorry, MODFLOW example 3, and it's just this one, EMF. Yes. So I can say insert. Now you have your map without any deformation or without any clipping or etc. So maybe you can have audio outputs like this, and I think that's what I have for today. And I believe you already have some knowledge about how we add files, import files, shape files, etc. in ModelMuse, how we run the model, and how we can input our results. So thank you for coming, and if you have any question, that's welcome.